In section 5.1, we're going to define energy and distinguish between different types of energy. We're going to distinguish between the related properties of heat, thermal energy, and temperature. We'll talk about what the differences between these things are. We're going to define and distinguish specific heat and heat capacity. And then we're going to finish off by performing some of the calculations that involve heat, specific heat, and temperature change. So chemical changes and their accompanying changes in energy are important parts of our everyday world. A couple examples of this is reactions involved in the metabolism of food, the energy we get from burning fossil fuels like gasoline, natural gas, and coal, and the production of all the useful products that we have from raw materials. Thermochemistry is the study of the heat absorbed or released during chemical and physical changes. So an example of energy being released from a chemical state is lighting a match. You form a chemical reaction between the strip on the box and the phosphorus coating on the matchstick, and that produces a flame that releases a lot of heat. But there are a lot of examples out there. There's the energy that we get from eating food, the gasoline that we burn to push our cars, and the processing of coal to create iron ore, and steel. So energy is the capacity to supply heat or do work. So if any time that anything gets hot or it absorbs heat or it's physically moving around, it's expending energy. There are three types of energy that we're going to talk about at first. There's the potential energy, the energy an object has because of its relative position, composition, or condition. So you can kind of think about potential energy as the energy that an object can potentially release. A bowling ball dropped from 3 feet is going to have a lot less energy than a bowling ball dropped from the top of a skyscraper, for instance. Kinetic energy is the energy that an object possesses because of its motion. So a baseball rolling across the grass doesn't have as much energy as a fastball that's been thrown at 100 miles an hour, for instance. Chemical energy is the energy that is contained within a chemical compound that gets released, like our match example. So one way to picture potential energy is if you think about waterfalls, right? That water has a lot of energy that's released when it's dropped down, and we can actually harness that by making dams and stuff to turn turbines when it drops and produce a lot of electricity doing that. So just like we had a law of conservation of mass, there's a law of conservation of energy. That says that during a chemical or physical change, energy is not created or destroyed, it's only moved from one form to another. So thermal energy is a subset of kinetic energy, and it's associated with the random motion of atoms and molecules. Temperature is the quantitative measure of this thermal energy. And basically, if something is hot, it means it has high thermal energy and the particles are moving really fast. Whereas if it's cold, it has low thermal energy and the particles aren't moving very much. So you can kind of see that in this example where our hot liquid has particles that are vibrating quite rapidly, a lot of them moving around. Whereas the cold liquid, they start to get a little bit closer together and they're not vibrating quite as much as they were before. We can measure temperature in a number of different ways. One of the classic ways is through expansion, whether that be a liquid inside of a glass that expands and rises up the glass tube, or this guy here that's called a thermocouple. You see these a lot in old school kind of thermostats and stuff like that. And basically what happens is as this heats, this coil will actually start to unwind. And as it cools, it'll contract down more. And by measuring the deflection across that, you can kind of tell how hot or cold it is. So heat is the transfer of thermal energy between two bodies at different temperatures. So a lot of times colloquially when we're talking about heat, we think of it as like something that's inside of something, but it's not really a thing in itself. It's thermal energy is the thing. Heat is the transfer of that, the movement of thermal energy from one thing to another. We can picture the process of heat here where we have a hot sink and a cold sink. And then when we bring them together, when we allow these molecules to bump up against those molecules, even through some sort of barrier here, eventually what's going to happen is they're going to reach thermal equilibrium. Eventually they'll both be at the same temperature and both sides will be moving relatively, the molecules on both sides will be moving at relatively the same speed. And that's due to the transfer of heat from the hot sink to the cold sink. Matter undergoing chemical reactions and physical changes can release or absorb heat. A change that releases heat is called an exothermic process. An example of that is a combustion reaction that occurs when using an acetylene torch. So anytime you have fire, that's an exothermic reaction. Lots of heat is coming off. But a change that absorbs heat is an endothermic process. This is like, for instance, when you have one of those cold packs you see in the medicine kits, first aid kits. Here we can see the acetylene torch in the instant cold pack. There's also the little heat warmers and stuff that you might see in the winter sometimes, and that's a chemical reaction that's occurring that's releasing heat, so that's an exothermic reaction. So, units of heat. Historically, energy was measured in units of calories, and a calorie is the amount of energy required to raise 1 gram of water 1 degree Celsius. And because the difference in temperature in degrees Celsius is the same as the difference in Kelvin, it could be called the amount of energy required to raise 1 gram of water by 1 degree Kelvin. Do be careful with that because it's only the differences in those temperatures that are equal to each other. It's not the actual absolute temperatures. This is a little confusing because we're used to seeing calories as far as food, but that's actually a different kind of calorie. It might be nice if they actually spelled it differently, but they didn't. Instead, they just put a capital C on it. And what that is actually 1,000 little c calories, or 1 kilocalorie. And if you're not sure what I'm talking about, this guy right here, that you'll see on the nutrition facts, has the number of calories in it, and you can see that that's written with a big C there. In most of our work, we're going to be using the SI unit, which is called the Joule. It is defined as the amount of energy used when a force of 1 Newton moves an object 1 meter. And it has a conversion from calories to joules, where 1 calorie is 4.184 joules. And you'll see that number popping up whenever we're working with water, the 4.184 joules number. So, heat capacity of a body of matter is the quantity of heat it absorbs or releases when it experiences a temperature degree change. So the temperature is either raised or lowered 1 degree Celsius. So here we can see that our heat capacity C is equal to the heat divided by the temperature change. So here's the important thing about this. The heat capacity is an extensive property. That means that if I have, say, a cup of hot water and an entire pot of hot water, even if they're at the same temperature and the change of temperature has been exactly the same, the pot of hot water is going to have a higher heat capacity because there's more of it. As you make the system larger and larger, the heat capacity will also get to be larger and larger and larger. Now, that's not very useful to us, right? We want a quantity that, regardless of the size of our system, we can apply it and we can know what the heat change is going to be, or calculate the temperature difference, for instance. So for that, we have the specific heat capacity. And what we've done here is we've taken the heat capacity and we divided it by the mass. Okay? So now we have a value that is per mass unit of our quantity. Okay? So even if the heat capacity rises because we have more and more mass, the amount of temperature change per unit of heat, or the amount of heat required per unit of temperature change, is not going to change gram per gram when you're using the specific heat capacity. This makes it an intensive quantity, and you'll see that we're going to be using this for the majority of our calculations. Here's an example of it. Due to its larger mass, a frying pan has a larger heat capacity than a small frying pan. Because they're made of the same material, both frying pans have the same specific heat. So one thing that we can do when we're using specific heats is have various ones for all of our different compounds that we're using. So we know that whenever we have a system that's just helium, it's going to have a specific heat of 5.193 joules per gram Celsius. A lot of our calculations are going to involve water, and you're going to see that number again, 4.184 joules per gram Celsius is its specific heat. Calculating heat. So the amount of heat that we're going to abbreviate with a Q entering or leaving a substance can be calculated by taking the specific heat capacity, multiplying it by the mass of the system, and then multiplying that by the change in temperature. And the change in temperature we're always going to calculate as the final temperature minus the initial temperature. So you can see that if the substance gains thermal energy, the final temperature is going to be higher than the initial temperature, then the value of Q is going to be positive. So when energy is going into the system, we get a positive heat. If a substance loses thermal energy, then the final temperature is going to be less than the initial temperature. Then the value of Q is negative. This is usually how I see this defined. However, if you guys do go on and see some other textbooks and some other disciplines besides chemistry, sometimes these are actually reversed. So it's always important to know what kind of definitions you're working under. But for all of our work, when a substance gains thermal energy, we're going to have a positive Q. And when that substance loses energy, we're going to have a negative Q. So a flask containing basically 800 grams of water is heated, and the temperature of the water increases from 21 degrees C to 85 degrees C. How much heat did the water absorb? So the first thing we need to know is our specific heat capacity. And that is a lookup thing, right? That would be like going back to this table and taking a look here and saying, oh, okay, water is 4.184 joules per gram Celsius. The next thing is multiplying it by its mass. And we were given that right in the problem, right? We were given water in terms of grams. It wasn't even a volume, so we don't have to mess with the density here to get the mass. We just plug that value in directly. Then we need to figure out what our delta T there. So it says from 2. So the 85 degrees Celsius, is our final temperature. That's going to go first. and we're going to subtract from it the 21 degrees Celsius. When we plug all those values out, we get a value of 2.1 times 10 to the 5 joules, which is pretty big, and that's the way that you should expect your joule values to look. It's a pretty small value. That's why often it will be written out as actually kilojoules. You'll do a little conversion at the end here and divide this by 1,000. Let's double check our units again. Here we've got joules per gram times degrees Celsius. We multiply that by grams. That cancels this grams here. We multiply that by degrees C. That cancels that guy down there in that denominator. The only thing we're left with is a numerator of joules. So you can see an example of harnessing heat energy here. This is a process where they take a whole bunch of mirrors like out in the desert and they kind of focus it all on one point in order to heat that water up to a boil. And then when they do that, it produces steam that they force through a turbine. It's kind of like a giant magnifying glass that you may have used when you were a kid to say, like, you know, set a leaf on fire or something cool like that. In section 5.2, we're going to be learning about the technique of calorimetry. Calorimetry is a technique for measuring the amount of heat that is either absorbed or released during a chemical or physical process. And basically what we're going to do is, it's difficult to measure these processes directly, so we're going to place them inside of some sort of medium that we can measure the temperature of very precisely. And we're going to then figure out how much this chemical process has either raised or lowered the temperature of that medium. And we're going to do this inside of a device called a calorimeter. And we're going to need to calibrate our calorimeter so that we know how much heat is required in order to raise the temperature by a certain amount or lower the temperature by a certain amount. So first we're going to start with a couple of definitions. We have the system. This is the chemical or physical change that we're interested in measuring that's going to be difficult to measure otherwise. And then we have the surroundings. This is all the other stuff that's around in our calorimeter that we are going to be able to measure the temperature of. So we're going to see a transfer of heat from the system to the surroundings, or in the case of an exothermic reaction, or we're going to see a transfer of heat from the surroundings to the system in the case of an endothermic reaction. We can picture that here, where we have our system releasing heat in an exothermic process, and that's going to go out to the solution that it's being suspended in, which is our surroundings. And then that's ultimately going to come to some thermal equilibrium. Or we're going to have the case where the system is undergoing an endothermic reaction and heat is moving from the surroundings into the system in this case. Eventually that goes to thermal equilibrium and the temperature of the surroundings has gone down. So what makes a good calorimeter? Our calorimeter has to be really well insulated. All the heat that is either released or absorbed, everything about our system and surroundings has to be insulated from the outside world. We can't let heat escape and we can't let it get inside our calorimeter. A lot of the times you'll see the classic experiment is the coffee cup calorimeter. This is where we just use like polystyrene cups to create a calorimeter. Here's an example of that. You can see you just kind of double up on the polystyrene cups and you fasten a little cap of some sort to the top there so that you don't have heat coming in and out here. We can measure the temperature with a regular thermometer, and we have this little stirrer. They put this little loop on the bottom so you don't hit that, and you just kind of work it up and down. Calorimeters can be quite a bit fancier than that, though. Here is kind of a analog to a coffee cup calorimeter. That's a commercial unit. It's made out of two concentric vessels that have a little air gap in them here, and that's causing the insulation. Still just a insulating cover, thermometer, and a stirrer there. Here we have something that's a little fancier than that. It's a little bit larger, still using kind of an air gap for insulation, but this one has a little mechanical motor here that's turning this guy, so it's continuously being stirred. And then you can put in a electronic thermometer here. This is called a thermocouple, and you can measure. Some of these are very nice. You can measure very small amounts of temperature change down to the thousandths place or more. So let's think about what's going to happen here with a kind of basic example. Let's consider that we have a hot piece of metal, we're going to call it M, and a cool water, W. If the metal is placed in the water within a calorimeter, so it's completely separated and isolated from the surroundings, heat's going to transfer from the metal to the water. The temperature of the metal will decrease, and the temperature of the water is going to increase. And then eventually they're going to come to thermal equilibrium, where they both have the same temperature. In a scenario like this, the heat released by the metal plus the heat gained by the water is going to sum together to be 0. These guys have opposite signs, so we can see that the heat of the metal is going to equal the negative heat of the water. They're going to have the same magnitude but different signs in this case. If we kind of picture what's happening here, we've got our metal inside of our calorimeter. That's our system. Heat's being released out to the water, which is our surroundings. Eventually they come to thermal equilibrium, and we can see that the thermometer's temperature has risen up because the water, the thing that we're actually measuring, got warmer. Let's see how we can actually put numbers to this, though, and quantify this. So if we have a 360 gram piece of rebar, this is like a steel rod used for reinforcing concrete. You've probably seen these before. And we drop that into 425 milliliters of water that's at 24 degrees C, so roughly room temperature. The final temperature of the water is measured to be 42.7 degrees Celsius. And we want to calculate the initial temperature of the piece of rebar. And we're going to make some assumptions here. We're going to assume that the specific heat of steel is approximately the same as that for iron. And we could find that value in table 5.1 in the textbook. And that all the heat transfer occurs between the rebar and the water because we have some insulation around it. So the first thing that we need to recognize here is that the heat lost by the rebar is going to be gained by the water, and therefore Q rebar is going to equal negative Q water. Since we're going to substitute in our definitions for heat. So we have the specific heat capacity of the rebar. We have the mass of the rebar. So we could look up the specific heat capacity for steel in table 5.1 to get the specific heat for the rebar. The mass of rebar was given to us in the problem. The delta T of rebar is part of the question that we're asking. We knew its initial temperature, or final temperature, but we don't know what the initial temperature was. Then we're going to have our C for water. This is going to be that 4.184 number that we were working with before. The mass of water was given to us in the temperature, and the initial and final temperature of the water was also given in the problem. If we expand out our delta T values here, we get this expression here, which looks a little complicated, but we now know pretty much all of these values except for the initial temperature of the rebar, which is what we wanted to know. So if we start plugging in all those values, the one that we got from table 5.1 for the specific heat of the rebar, the mass of that rebar, its initial temperature or final temperature, which is going to be the same as the water, because remember they came to thermal equilibrium, right? And then we have the specific heat for the water, we have the mass of the water, we know that the water was initially at 24.0 degrees Celsius. Now all we need to do is some algebra, right? We're going to have to distribute these values through here. We're going to have to gather all the terms with Ti on the other side and then divide through. We can determine that the initial temperature of the rebar was 248 degrees C. So and that was the initial temperature of the rebar. I have an example in the homework problems where I go through the algebra to do these kind of problems. So if you're a little curious about that, you can check that. So in our example before, we weren't doing calorimetry properly, right? But we can see that we can extend the exact same principles to actually doing calorimetry, even if we're mixing solutions. And it's not necessarily completely clear where the system is, like it was in the example with the metal. So let's take a look at an example here of that. When we are mixing 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH, and both of those solutions are at 22 degrees Celsius. We add them into our coffee cup calorimeter, and the temperature of this mixture reaches a maximum of 28.9 degrees Celsius. So in this case, our system are the molecules of HCl and NaOH that are combining together to form NaCl and water. We can't see it like we did with the metal before, but the math behind it is exactly the same. So we're going to have that our Q reaction, the heat given off by this reaction, is going to be equal to the negative Q of the solution. We're going to input our definition for heat into Q solution. We're going to have the specific heat capacity of the solution times the mass of the solution times the temperature change of the solution. And now we're going to make a couple of assumptions here. So our first assumption is that 1 molar HCl and 1 molar NaOH, they have a specific heat capacity that's roughly the same as water, 4.184. Given that most of these solutions, most of the atoms in that solution are water, it's not unreasonable. It's going to be very close to that value. We're then going to also make the assumption that those two solutions have a density of about 1 gram per milliliter. So the 100 milliliters that we have altogether, 50 mils of HCl and 50 mils of NaOH, is going to weigh about 100 grams. And then we have our change in temperature, which is going to be the difference between that final temperature when we mix the two together and the initial temperature that they were both sitting at, 22 degrees Celsius. If we do all that math out, we're going to see that that reaction released 2.9 times 10 to the 3 joules. We do need to remember, though, that that was the Q for, or that we were looking for Q reaction, right? This was an exothermic reaction, so we should be getting a negative value, right? Heat was released from the system and into the solution. Q reaction equals negative Q solution. We get negative 2.9 times 10 to the 3. So bomb calorimetry. This is pretty useful in the sense that you can basically make almost anything combust completely given the right conditions. And so it's a good way to be able to do calorimetry with things that aren't necessarily going to react very quickly or easily in any kind of sense. And basically what we're going to do is we're going to take a vessel that they call a bomb. It's usually made out of very thick metal alloys, very tough little guys there. And we're going to charge that up with a whole bunch of oxygen. So like something like 25 atmospheres typically of oxygen would go into these little bombs here. Okay, so that's just waiting to burn up. And you'll put your sample in a little cup like this. And then there's these two electrodes, and that's going to like make a little spark. So you put the two electrodes kind of close to the cup, and with all that oxygen in there, you ignite it, and it burns this up completely. And then the vessel heats up, and the water heats up, and we can figure out how much energy was inside of that sample. This is what they do often with things like food or fuels and stuff to figure out how much energy is going to be released. Another example of a calorimeter is a whole body calorimeter. It's like a giant calorimeter that they put people in and basically measure how much energy is coming off of them given how much food that they ate. And in this sense, they come up with a value that's known as the nutritional calories. So you eat a certain amount of energy, but you don't necessarily use it all. Some of that food just goes completely unwasted and goes right through your body, and it never really gets burned as fuel inside your body. So they have this idea of the nutritional calorie, which is the energy unit used to quantify the amount of energy derived from the metabolism of food. So section 5.3 is going to be a big one. This is where we're really going to jump into thermodynamics, starting with the first law of thermodynamics. We're going to define some values such as enthalpy, and we'll talk about how that's a state function. We'll learn to write and balance thermochemical equations and how to do enthalpy calculations using a few different techniques that we'll have. First off, we'll remember thermochemistry is a branch of chemical thermodynamics. It's the science that deals with the relationship between heat, work, and other forms of energy. We need to start to think about different substances as acting as reservoirs of energy. So they contain energy that can then, and we can add energy to those substances. We can remove it from them. And when we add energy to a substance, what's happening is we're increasing the kinetic energy of each of the atoms or molecules that make up that substance. So let's start off with defining internal energy. The total of all possible kinds of energy present in a substance is called the internal energy, and that is abbreviated with a capital U, very ambiguously. As sometimes you'll see a capital E, but in chemistry you're typically going to see a capital U. Now, we can add up all of the different kinds of energy within a substance and find out the exact internal energy of the substance. But typically, we're really not very concerned about that. What we want to know is how the internal energy of a substance is changing. And for that, we have this relationship between the change of the internal energy of a substance and the heat and work that are either added to it or removed from it. And this is what is called the first law of thermodynamics. So we have a sign convention that we need to follow. energy can be transported into the system, resulting in an increase in internal energy. If this is true and the system absorbs heat, we're going to have a positive Q value. And if instead the surroundings do work on the system, then we get a positive work value. Energy can be also transferred out of the system. Okay, that system can release heat or it can do work on the surroundings. Both of those values will be negative. We can see that here where we have our system in the center, and when the internal energy is negative, work and heat are being removed from the system. Whereas if the internal energy is gaining internal energy, work is being done on the system, heat is going in. Now, I will mention that this is a little bit of an oversimplification. You could have a process whereby, say, heat goes in and work comes out, but if the work coming out is not as large as the heat going in, the system ultimately gains internal energy. Similarly, you could say have a system where work goes in and heat comes out, but there's more heat that comes out than work goes in, and then the system winds up losing energy. So you have to realize that all of these are possibilities. So the work that chemists are mostly concerned about is called expansion work, sometimes called pressure volume work. And this is basically where a system pushes back on the surroundings against a restraining pressure. This is happening all the time. Your body is pushing back on the pressure of the atmosphere, pushing in on it right now. And so there's this type of expansion work that keeps your body from just being crushed by the atmosphere around it. This is happening around us and to differing degrees in differing systems. So if we consider an example of this, we could have a system inside of the combustion engine. For instance, we could define the system to be the gasoline and the oxygen. And the surroundings is pretty much everything around that, including the engine. This reaction is exothermic. It's going to give off heat, so Q is negative. And the reaction pushes the pistons out, right, by expanding. So work is negative. And ultimately the gas and oxygen have decreased their internal energy by releasing it out into the world. So internal energy is an example of a state function or state variable. The value of a state function depends only on the state that the system is in and not how that state is reached. So we only have to have information about what we started with and what we ended with. It doesn't matter the path it took between the two. An example of this might be altitude or elevation. For instance, your potential energy difference will be the same going from the base of the mountain to the top, regardless of what path you took to get there. Okay, you're still going to have the same difference in potential energy, just so long as we know the end point and the beginning point. So chemists are mostly concerned about enthalpy, and we're going to talk a little bit about what that is. So enthalpy is defined as the sum of a system's internal energy and the mathematical product of its pressure and volume. Okay? The enthalpy is also a state function, and unlike internal energy, we cannot at all calculate the absolute enthalpy of a substance. But again, we're not very concerned about the enthalpy inside the substance. We're concerned about how the enthalpy changes during a chemical or physical process. So, commonly chemical and physical processes occur at constant pressure. At constant pressure, we can make the substitution that P delta V, pressure times the change in volume, is equal to the negative work done by the system on the surroundings. And it's always going to be true that the arithmetic signs of delta V and W will always be opposite. So if you have a positive delta V, you're going to have a negative W. If you have a positive W, you're going to have a negative delta V. So that's important, because what we're going to do next is we're going to take this delta U and we're going to substitute in our original definition here of QP, heat at constant pressure, plus W. And then we're going to substitute in for P delta V this negative W. And what we're going to see is that work is going to cancel, and that the change in enthalpy is equal to the heat either added or released from the system at constant pressure. So we've already seen that we have good ways of measuring heat, and this is going to give us a good way of measuring this thermodynamic quantity, enthalpy. So why enthalpy particularly? So a lot of times chemists are going to just do stuff in the open air at their lab benches and stuff. This is under normal atmospheric conditions, and the external pressure is pretty constant. The pressure from room to room might vary a little, but not much, and not in any real significant way. So if only the work is done caused by expansion and contraction, then the heat flow and the enthalpy delta H for the process are equal, and this makes enthalpy a very convenient choice for determining heat and for measuring heat to determine enthalpy change. So, thermochemical equations. Basically, this is the same kind of equation that we've been using before, only now we're going to add the change in enthalpy during that process at the end. And we're going to write it kind of like this. So we're always going to write this out. And you'll notice a lot of the time that you don't always have those least common multiple coefficients here. Because you're going to see is that this enthalpy is going to change when written like this, because it's an extensive property when written like this. Okay, if I say had two H2s plus O2 is going to yield two H2Os, well then this delta H value is going to double. All right, we will have situations later where we make this into an intensive property. And just like we did that with specific heat, what we're going to do is we're going to divide this by some quantity that makes it intensive. In this case, we're going to divide it by the number of moles that have either reacted or are produced. So you need to watch out for that later, and we'll show some examples of that. So if the direction of a chemical equation is reversed, the arithmetic sign of delta H is also reversed. So you can see that down here when we switch it so that we have our product starting and that goes to the initial reactants, we're switching the sign of delta H. Here is what I was talking about before. If the coefficients of the chemical equation are multiplied by some factor, the enthalpy change must also be multiplied by that same factor. So if we multiply everything by 2, we wind up multiplying the enthalpy by 2. If we multiply by a factor of 1/2, we multiply the enthalpy by a factor of 1/2. The change of enthalpy of a reaction depends on the physical state of the reactants and products. So typically, we're going to show these. For instance, this would be different if we were producing, water vapor as a gas, or if we added liquid oxygen here. And you can see the difference between producing liquid water and producing water as a gas. Obviously, so some additional energy winds up being released when we go from gaseous H2O to liquid H2O, and you can see that results in a more negative enthalpy change. Let's look at an example here. A gummy bear contains 2.67 grams of sucrose. We have the formula for sucrose there. When the gummy bear reacts with 7.19 grams of potassium chlorate, 43.7 kilojoules of heat is produced. Write a thermochemical equation for the reaction of 1 mole of sucrose. So we're going to start by writing a balanced equation for this reaction. And it's a little bit of a tricky one, but I did it for you down here. We're going to start off with this guy. We're going to add 8 moles of our potassium chlorate. This is a combustion reaction, so we're going to wind up with CO2, water, and finally potassium chloride salt as the breakdown product of our oxidizing agent there, potassium chlorate. First, we'll determine the number of moles of the reactant. So we need to know how many moles of sucrose we had. We'll divide that by its molecular weight, which we saw how to calculate previously. And then we'll figure out the number of moles of potassium chlorate. And then we'll determine the ratio of one reactant to another here. We can see that we have 7.52 times the number of moles of potassium chlorate as we do sucrose, and that we actually needed 8 times the amount given our stoichiometry over here. So our limiting reactant in this case is going to be the potassium chlorate. Next, what we're going to need to do is to decide. So we take the limiting reactant, our potassium chlorate, and we're going to use that to determine our delta H change. And what we're going to do is come back here and look at the problem. We see that there's 43.7 kilojoules of heat is produced. So that's all of our heat right here. And we're going to divide that by the number of moles of potassium chlorate. And we'll see that for every mole that is reacted, we got 744 kilojoules of heat released. Now, because the equation as written represents the reaction of 8 moles, the enthalpy change is going to be a little different. Now we've figured out how many kilojoules of heat get released per mole of potassium chlorate. We need to multiply by the amount of potassium chlorate we'd like to react, and we can see as written that equation is going to produce 5,960 kilojoules of heat. So enthalpy changes are typically tabulated for reactions in which both the reactants and products are at the same conditions. This is called the standard state. So the standard state is a commonly accepted set of conditions used as a reference point for the determination of properties of, under other conditions. So what this basically allows us to do is that if we can just start to collect data about the enthalpy values of different things under a certain set of conditions, because if we tried to just collect data under all conditions, it would just be too much. And it's really ultimately kind of unnecessary, and we'll start to see why that's true. It is important to know what the standard state conditions are. So under the IUPAC standard, the standard state conditions are 1 bar of pressure, and solutions will be at 1 molar concentrations. So when we're talking about the enthalpy change at the standard state, you're going to see a superscripted O in the enthalpy change. Like you see down here, this little guy right there. The usual temperature that we're going to be talking about is going to be 298.15 Kelvin, or 25 degrees Celsius. And so we got 1 bar, 1 molar solutions, 298.15 Kelvin. So the enthalpy changes for many types of chemicals and physical processes are available in the reference literature. That's where we've started to figure out what the different values are at this standard state. We're going to recall that delta H is an extensive property, and that means that it's proportional to the amount of substances involved. So what we're going to do is what I was discussing earlier. We're going to make it an intensive property by normalizing it to a per mole basis. We're going to take the typical delta H and we're going to divide it per mole. So the standard enthalpy of combustion, for instance, is the enthalpy change when exactly 1 mole of a substance burns, combines vigorously with oxygen, under standard state conditions. So even though when you burn something, it's going to produce different amounts of moles of CO2 and water and possibly some salts or something like that, we're going to normalize it to the number of moles of a particular substance that we started off as our reactant with oxygen. All right, let's look at an example of that. The enthalpy of combustion of ethanol is negative 1,366.8 kilojoules per mole. This is the amount of heat produced when 1 mole of ethanol undergoes complete combustion at 25 degrees Celsius and 1 atmosphere of pressure, yielding products also at 25 degrees Celsius and 1 atmosphere of pressure. And we can see an example of how we would write that down here. We're going to have our ethanol. It's in a liquid state because that's the standard state of ethanol at 25 degrees and 1 atmosphere, plus the stoichiometric amount of O2, whatever that might be for the initial reactant. In this case, it's 3 O2s. We're going to produce CO2 and water exclusively because we only started off with a carbon, hydrogen, oxygen compound. And that's going to release enthalpy under standard conditions. So we write the little circle right there of negative 1,366.8 kilojoules. So we have tables and tables with tons of these values. You take any substance, you can see what the combustion reaction would be for it, and you can see what the enthalpy of that combustion at standard state would be. There's a more complete table at the end of the text that you will need for some of the problems. So, as that previous figure suggests, the combustion of gasoline is a highly exothermic process. We want to determine the approximate amount of heat produced by burning 1 liter of gasoline. We're assuming that the enthalpy of combustion of gasoline is the same as that as isooctane. Where that assumption's coming in is that gasoline is actually a mixture, so it's kind of a more complicated problem than this, but a large amount of it is isooctane. And we're going to need to know the density of isooctane, and that is 0.692 grams per milliliter. So let's take a look at this. So if we had a liter of isooctane, one of the first things we're going to need to know is how many moles that is. So we start off with that liter. We convert it into milliliters. So 1 liter is 1,000 milliliters, right? Now we need to go through the density to figure out how much mass that is. So we'll times it by 0.692 grams per milliliter. So we would know if we did this calculation right here that there's 692 grams of that isooctane in 1 liter. Then we need to figure out how many moles we have. So we would have had to calculate the molar mass of the isooctane to get the moles. And then finally we look up this value that we could see in table 5.2 that says that for every mole of isooctane burned, we're going to get negative 5,460 kilojoules. We'll multiply by that, canceling our moles, and we see that that 1 liter produced negative, well, what would that be? 33,100 kilojoules. Quite a bit of energy. So one thing that can be kind of interesting is the idea of renewable fuels from algae. This is a little vignette that was in the book that I thought was quite interesting. Instead of burning fossil fuels, one thing that they can do now is actually genetically modify the algae, grow it in these large troughs, harvest it, then they centrifuge it to extract it out, and then they're able to process out high-grade fuels from it. Quite interesting stuff when you're thinking about all the carbon that we're releasing on the atmosphere to produce climate change. This actually starts off the life cycle of our fuel as taking the carbon out of the atmosphere. A very natural process. So another form of standard enthalpy is called the standard enthalpy of formation. This is the enthalpy change for a reaction in which exactly 1 mole of a pure substance is formed from its constituent free elements in their most stable states. A lot of assumptions underneath there. Under state conditions, standard state conditions. All right. So, for example, if we have CO2, we're going to start off with carbon in a solid state because that's the stable state of carbon at standard conditions. O2 would be a gas. We're going to combine those together to produce CO2 as a gas because, again, that's the state we would typically see it in. And we're going to get that the enthalpy of formation of this reaction, which is the same as the standard enthalpy for the reaction as written, is going to equal negative 393.5 kilojoules. This is essentially a combustion reaction, so it's not surprising that this is exothermic, but a lot of times you're going to see that the standard enthalpy of formation is really going to be an endothermic process. You have to put energy in order to produce something from its elements. So an important thing to note here is that the standard enthalpy of formation of an element in its most stable form is equal to 0 under standard conditions. So to produce CS, for instance, that's 0. O2 gas, it's going to be 0. So sometimes you can, kind of skip looking it up in the table if you're sure that that's going to be a 0. All right, so let's look at some examples here. We're going to write the heat of formation reaction equations for, we have ethanol there as a liquid, and then we have calcium phosphate as a solid. we're going to remember that the change of enthalpy of formation reaction equations are for forming 1 mole of the compound from its constituent elements under standard conditions. So, to produce ethanol, we're going to need 2 moles of that solid carbon in the form of graphite, for instance. It's one of the allotropies of carbon, plus 3 molecules of hydrogen gas, plus a half of a molecule of oxygen gas, in order to have the stoichiometry correct and have a 1 in front of here. That's what's important. You could have balanced this in any old way that you would have liked, and then just divided each of the coefficients by whatever you had in front of ethanol here, but you want your product to have a 1 in front of it here to be when you're calculating the enthalpies of formation. For calcium, we have a similar process to produce the calcium phosphate, and again, we're getting that 1 in front of the calcium phosphate. There are 2 ways to determine the amount of heat involved in a chemical change. We can measure it experimentally. We saw how to do that with calorimetry. Or we can calculate it from other experimentally determined enthalpy changes. Some reactions can be very difficult, if not impossible, to measure directly. But what we can do is we can just have like kind of a bank of very simple reactions, and then we can use this technique called Hess's law in order to use those simpler reactions to figure out the more complicated reactions. So Hess's law states that if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. And this is kind of an extension of the idea of the state function. It doesn't matter what processes we put together, so long as we start with the thing that we have and we finish up with what we want. So let's take a look at an example here. We can think of the reaction of carbon with oxygen to form carbon dioxide as occurring either directly or by a 2-step process. So the direct process would be carbon solid plus O2 gas equals CO2 gas. We've already seen that. In the 2-step process, first carbon monoxide is formed, and carbon monoxide reacts further to form carbon dioxide. So in this scenario, we're going to first add 1 oxygen to our carbon to make carbon monoxide, and in the following step, we're going to take that carbon monoxide, add the other oxygen, and form CO2. And if we knew the standard enthalpy changes for both of those reactions, what we can see is that when we sum these 2 together, we'll get this down here. And when we cancel the COs, our spectator species, just like we did when we were doing redox reactions, we'll get our original equation, and if we sum these 2 together, we'll see that that equals the delta standard enthalpy change that we already knew CO2 to have. Here's a diagram of this. So basically what we were saying is that carbon plus oxygen going down to CO2 is going to have the same enthalpy change as going from carbon to oxygen, and then carbon monoxide to CO2. So we can also use Hess's law to determine the enthalpy change of any reaction if the corresponding enthalpies of formation of the reactants and products are available. The stepwise reactions we consider are decompositions of the reactants into their component elements for which the enthalpy changes are proportional to the negative of the enthalpies of formation of the reactions, followed by recombinations of the elements to give the products with the enthalpy changes proportional to enthalpies of formation of the products. So that is a big statement there. Let's take a look at the math because I think it's actually a little bit easier. So basically what we're going to do here is we're going to look up in the table all of the standard changes of enthalpy of formation for our products. We're going to multiply each one of those by the stoichiometric coefficients. That's what this n is here. You know, if you're looking at the equation, what are the coefficients in front of that product? Okay. And then we're going to go ahead and we're going to sum all of those together. That's going to be one value. We're going to do the exact same thing for the reactants. We're going to sum them all together. That's going to be another value. Then we're going to take the product value that we got and we're going to subtract out the reactants value that we got. Let's take a look at an example. What is the standard enthalpy change for the reaction when we have 3 nitrous oxides plus water as a liquid? That's going to go to 2 nitric acids plus an NO gas. What is that going to be? So if we went to the table, okay, what we would see is that so we've got to start with our products, right? So we're starting on the right-hand side of this equation. If we looked up nitric acid, we would see that it has a standard enthalpy of negative 207.4 kilojoules per mole. We multiply that by the coefficient of the nitric acid, that number of moles, and that's going to be one of our quantities. It's 1N delta H, okay? Then we do the exact same thing for NO. We look up its value, we multiply it by its coefficient, we add these two together. That is this whole big piece right here, all right, including the sum. And then we do that exact same thing for the products. And we take this whole first value as represented by this whole top row right here. We subtract out this whole second value here. And we get the actual standard enthalpy change for that reaction. That is everything that I have for this presentation. I have a lot of good examples in the homework of these problems, and I would encourage you guys to take a look at them.